Okay, in this video we're going to talk about symmetry and where we can identify symmetry both on our functions and in our non-functions, and the process in which we can identify symmetry for both functions and non-functions. So let's go ahead and just look at a couple functions and we will analyze them and see if they have any symmetry. When we talk about symmetry, we're going to look at three different types of symmetry. We're going to talk about symmetry with respect to, so when you see WRT, you're going to see that consists of, that abbreviates for with respect to. We're going to have symmetry with respect to the x-axis. We can have symmetry with respect to the y-axis. And then we could have symmetry with respect to the origin. So we're going to note that we have symmetry in regards to three different types, or three different venues. We have symmetry with respect to the x-axis, the y-axis, and the origin. So let's go ahead and analyze our function f of x is equal to x squared. F of x is equal to x squared. So this is a function that is a parabola, and it opens up like such, and it's going to intersect at our origin. It's going to continue on to this opposite end in quadrant 1. So, you know, being that I can't draw things perfectly, if I were to take this image and I were to rotate, if I were to rotate it, and and right now it says rotate 90 degrees. If I rotate it 90 degrees, I would have something that looks like this. If I rotate it another 90 degrees, I would have it completely upside down. And if I were to do it one more time and two more times, that'd be a total rotation of 360 degrees. So that's working. That's me rotating this function in a counterclockwise, in a clockwise direction. However, when we talk about symmetry with respect to, for example, the y-axis, assume that I put a corkscrew on top of my y-axis and I turned my graph 180 degrees. So I turned my graph 180 degrees. Hopefully we could see if let's say I would turn it this way. So I'm turning it this way out of the page 180 degrees. And symmetry to the x-axis means that if you can rotate your graph 180 degrees and you have the exact same picture, your function contains symmetry with respect to the y-axis. And also we can recognize that if I were to draw a vertical line through the y-axis, or if we were to let the y-axis be a vertical line, this axis would bisect our function into two equal parts. And we would have the same image on the left side as we do on the right side. Therefore, we can conclude that f of x equals to x squared has symmetry with respect to the y-axis. So this function has symmetry with respect to the y-axis. Let's go ahead now and talk about a different type of symmetry. And in this section, in this next part, we'll talk about symmetry with respect to the x-axis. So symmetry with respect to the x-axis. So drawing our graph one more time. Let's go ahead and analyze the equation x equals to y squared. So let's analyze the equation x equals to y squared. When we go ahead and we plug in points, if we plug in points, this is not as easy for us to graph, and we're not going to work with as many of these because when in fact a graph has symmetry with respect to the x-axis, it's not going to be a function. So if I were to plot this, let's do a plot here. So I have an x and a y. So I'm going to let y be 0, therefore x would be 0. If I let y be 1, x would be 1. If I let y be negative 1, x equals to positive 1 as well. So I let y be 2. Plugging this in, just so we can see, we would have x equals to 2 squared. So x would equal to 4. If I were to plug in negative 2, we would have x equals to negative 2 squared. So that would also give me a value of positive 4. Ultimately, what this graph is, this is a picture of that same parabola we had before, but now it opens to the right. It opens to the right. So hopefully we recognize if I were to draw a vertical line through this function, that it would intersect more than once. I'm sorry, not through this function, through this graph. It would intersect more than once. Therefore, we know x equals 2y squared is not a function. And that was not specifically a question here, but you will note that in this circumstance now, if I were to put a corkscrew here up on top, and I were to rotate this guy 180 degrees, we would have the exact same graph. So this guy has symmetry with respect to the x-axis. And if I were to draw a horizontal line through the center of this function, it would bisect this graph in two equal parts. So this guy here has symmetry. So x equals to y squared. X equals to y squared has symmetry with respect to the x-axis. So that's the second type of symmetry we expect to see in our graphs. And then the last type of symmetry we expect to see is symmetry with respect to the origin. Symmetry with respect to the origin. I'm a little too far there. So symmetry with respect to the origin. Origin. Symmetry with respect to the origin. So let's examine f of x is equal to x cubed. So I'm not always, as I said before, perfect at drawing these graphs. So this graph will start down here in quadrant 3. And it will eventually intersect at 0, 0, and then continue on out into quadrant 1. So it looks something like this. Yes, I believe it looks something like that. So yeah, something like that. So this is the graph f of x equals to x cubed. And first of all, I always like to make a little note here. In order for a function, notice I called it a function, to have symmetry with respect to the origin, it must intersect the origin. So in order for your graph or function, as I said function here, to have symmetry with respect to the origin, it must intersect the origin. So clearly here we see that f of x equals to x cubed does intersect the origin. So that's one of our first constraints that we have to meet, is that it's going to have to intersect the origin. Now notice I'm going to highlight just the graph itself. I'm going to have to highlight both of them. Let's see if I can do that here. Oh, I can't. So I'm actually going to delete that, and I'll redraw it one more time. So let me delete this so I can redraw it all as one. So let me go back and redraw. So it's going to come down here. Hopefully I can do this correctly, because otherwise it will. Oh, I let my pen up. Starting, there we go. No, that's not very good. Okay, so one more time. And continuing off to pause and fade. There we go. So now, as I were to grab this function, I'm going to rotate it 90 degrees right, and then rotate it another 90 degrees right. And notice, I think I did a pretty good job actually. Notice we got pretty much the exact same, function. So we rotate 90 degrees right, and then rotate another 90 degrees right. And if you can rotate 90 degrees plus 90 degrees, which is 180 degrees, if you can rotate your graph 180 degrees to the right or left, and you have the same function, you have origin symmetry, or symmetry with respect to the origin. And notice we were able to do so. We were able to rotate this guy 180 degrees to the right or to the left, it does not matter, and we have the exact same function. So we have symmetry with respect to the origin.